Alright, let's go over numbers 2 and 3 from the Chapter 6 review. So they describe this region, and then they're going to ask us to do several things here. So part A, find the area of R. So just the area of this piece between the horizontal line y equals 4 and then this function f of x here. So of course, the easiest way to do that, simplest way to do that, is to simply say, well, it's the area between the curves. So that's the integral of the function on top minus the function on the bottom. And then, of course, I need to know the intersection points. And if you just go ahead and graph this, you'll see that this is, in fact, 0, and this one is 2.3. So those are that's my interval there from 0 to 2.3. And then if you just do that on your calculator, you'll get 3.218 units there. Part B, find the volume of the solid generated when R is rotated about the line y equals -2. So just going to draw a very rough and inaccurate picture of where y equals -2 is. I'm going to just say it's here just so that I can fit it. Okay. Certainly that's not to scale. But I'm rotating around that line. So when I'm thinking about my region here and spinning it around, I can see that this is going to be a washer because this is the line I'm spinning around. This is the center of my shape. My region never touches that. So there's going to be a hole throughout. Sometimes you have that like 1 point intersection and we say, okay, it doesn't always touch, so there's a hole. Well, in this case, there's just a huge gaping hole. It never touches. So I want to think about my basic washer formula here as the integral pi times the integral from a to b of my big radius squared minus my little radius squared dx. The idea being that we've sort of factored out the pi and the h for each cylinder, and we're subtracting them. We're subtracting out that core. And big R is simply the distance from the center of rotation, the axis of rotation, to the farther away place, the farther away side of my region. Well, I know that this distance, not to scale, is 2. And then from the x-axis all the way up here is 4. So big R is 6. Six squared minus, now it's from the center of rotation, the axis of rotation, to the closer piece, which that's not constant. That changes depending on where we are with our shape. But it's just the function value. If I think about it the same way, okay, this is 2, and then up to the inside. Well, that's the function value. So it's 2 plus f of x. I'm just going to write it like that. 2 plus f of x squared dx. And I'll be very careful when I enter that into my calculator. And if I do that, I should get about 98.868. So 98.868. Part C, now we're going to rotate it around the line x equals 4. Somewhere over here. And now the big switch here is that, of course, now I'm rotating around a vertical axis, which means I could change my washers and do them horizontally so that I go, okay, I have a hole, so I go to the outer edge, that's big R, and then the inner edge, that's little r. The problem here is that big R and little r are defined by the same function. This is not an invertible one-to-one function, so I can't just turn it into y. It won't work for me there. So my other option is to do shells and keep my rectangle vertical, which I'll do. So the basic formula for shells is the integral from a to b of 2 pi r times the height times dx. And the radius is just, okay, if I were to draw a rectangle in here, call that a rectangle, the radius is how far that rectangle is from the center of rotation. Well, again, I'll think about it in two pieces. From the y-axis to my rectangle, that's x by definition. How far you go right or left from the y-axis is x. And then from the y-axis all the way to my center of rotation is 4. So you've got 4, you've got x, and then you've got the difference here. My radius is 4 minus x. I'm going to go ahead and factor the 2 pi out. And then my radius is 4 minus x. And my height is just the height of this rectangle, which is the same as it was here, 4 minus the function value. 4, I'll do it again the other like I did in the last one, 4 minus f of x dx. Also, I forgot to write in the last one, the interval is still 0 to 2.3 because we're still in terms of x, and the interval is simply saying, okay, where do I start and stop adding up these things? So you're going to start at 0 and you're going to stop at 2.3. And if you carefully plug that into your calculator, you will get 49.877. All right. If you need to pause and write any of that down, please do that, because I'm going to erase that before we go on to part D. All right, part D is another volume, but in this case, it's one of those where we're imagining we're kind of sticking shapes onto the region, and we know what the area of a cross section would be, and so then we have to find that area and then multiply by dx to give it our width. Now this is a weird shape that we've described here, but that's sort of intentional. So what we're saying is that I'm going to take my green rectangle here, and I'm going to imagine that that's one base of an isosceles trapezoid. One base on R, so that's that, and then base 2 having a length twice that. Okay, so I drew my trapezoid upside down. So it's going to be like this. So this is base 1, and that's the piece that corresponds with this. And then the rest of this is sort of sticking up off the page in that format. So here's base 2. And then they say that the height is 3. So the area of any one trapezoid is 1/2 base 1 plus base 2 times the height. Height is 3, so that's going to be 3/2. And now if I write this B1 plus B2, B1 is again the length of this rectangle. Well, that's again 4 minus the function value. So that's 4 minus, I'll just say f of x. We've been doing that in this one. And then base 2 is 2 times that. And so that's the area of any one given rectangle. I think I'm going to clean that up a little bit. So we have 3/2. If I distribute the 2, that's going to be an 8. And then I have this original 4 here, so this is going to be an 8, and then the 4, and they're adding. None of that's going to be negative. So that's going to be 12. And then for the function, you've got a minus f of x, and then distribute that too. It's a minus 2f of x. So that's going to be 12 minus 3f of x. Yeah, I think I'll just leave it like that. And so that's the area of any one particular of these trapezoids. Plug in x, and that's going to give you the area. I then need to multiply by dx to give it an infinitely thin width, and then add all infinitely many of these up. So my integral here is going to be, I'll pull the 3/2 out, still from 0 to 2.3, because it's still this region R, and then of 12 minus 3f of x dx, and I believe we're going to get 14.482 approximately here. Kind of a weird one. We haven't done that particular shape yet, but that's why I think it's a good one for the review to kind of emphasize, hey, it doesn't matter what type of shape you have, you can do this for anything. Once again, if you want to pause and write that down before we go over E and F, because I'm going to erase that all. Part E wants the average value. We have a formula for that. 1 over b minus a. It's the integral from a to b. Sorry, I'm getting ahead of myself there. A to b of the function. In this case, a and b are 0 and 4. So 1/4 the integral from 0 to 4 of f of x dx. On your calculator, you should get 18.4. And then f, the arc length, so once again we have a formula for that. It's the integral from a to b of the square root of 1 plus the derivative squared dx. 0 to 4, 1 plus the derivative would be 4x cubed minus 6.9x squared dx. Plug that into our calculator and we get 115.487 if I plug that in correctly. All right, let's scroll up a little bit here. I think we do this last one without too much difficulty. It's been a while, but the intermediate value theorem, and there'll just be one little part of your test that requires you to talk about the intermediate value theorem, so if you just remember it, you'll be okay. So I like to think about this at the graph here. So I've got f of negative 3 is negative 1, f of 6 is positive 3. Which of these is guaranteed by the intermediate value theorem? And all the intermediate value theorem says is if you have a continuous function and you know these two sort of endpoints, then for any y value in between these, there has to be at least one x where the function hits that value. So this first one says f of 0 equals 0. Now at some point we do have to cross 0, but do I know that it happens at 0? No. So that's out. The second one says the derivative has to be 4/9. Well, the intermediate value theorem doesn't say anything about the derivative. That's the mean value theorem. So that's out. Now f of c equals 0 for at least one c between negative 1 and 3. Well, now that sounds right because I don't know that we equal 0 at 0, but for some value, yes, we have to get from this point to this point. Literally, watch my laser there. I can't get up there and get to that other point unless I cross the x-axis. The problem with this one is they gave you the wrong interval. This is the interval of the y-coordinates, negative 1 to 3. It needs to be the next one, which is the same thing, but the interval of the x-coordinates. Between this x and this x, we must, yes, somewhere cross the x-axis. So it is this one. It is D here for me. But just to say why it's not the last one, especially because I think it might shuffle for you and this wouldn't be the last one. This is saying that the y value always has to be between these two values. Well, that's not true. We could certainly go way up here and then way down and then back and get in there. We still hit every single value in between, which is what the intermediate value theorem says, but we just happen to hit several other things as well. So, no, we don't always have to stay in there. There's nothing that says that that would be true. All right, that's the review.